In today's video, we're going to do alcohols for the first year of A levels. Okay, there's another alcohols in second year, which goes on a little bit further than what we do. Okay, this is in module 4. The next one is in module 6, if you want to have a look at that. So solubility, let's have a look straight away. Alcohols have high solubility in H2O. So what I'd like you to do is stop the video and I would like you to draw a hydrogen bond. And we'll go through quickly how to do a hydrogen bond, quite quickly indeed. Okay, so high solubility due to hydrogen bonding. So if I do this, actually, let's just put that to the side. Okay, and go from there. So basically all we do is we take an alcohol. So let's take an alcohol and I'm going to draw the OH like that. So just to make it obvious. That could be R, okay, just any alkyl group. I've chosen CH3. You then line up your water like this. Okay, and then you put your dipoles on. So the next stage is put your dipoles on. Notice I've lined the H with the O and the O with the H. That's because they have opposite dipoles. So there we go. Okay, and there we have our dipoles. So I want stages. If you're going to draw these, you do it in stages. The first stage is draw the compounds. Next one is draw the dipoles. After you've drawn the dipoles, then you draw the bond. Now you can draw the bond between the O and the H here, or the O and the H here. Doesn't matter which one you do, but you draw the bond between there. So I'm going to draw, and you can draw it as dashes or you can do it like this. Okay, there you go. So there you go. You've done your hydrogen bond, you've done your dipoles. Now the last thing you put on, if you haven't put it on already, is you put on your lone pair. So the bond should go from one of the lone pairs. I'll put the lone pair in there a little bit late, but it goes from the lone pair up to there. Now if you're doing the other drawing, you could do it from the lone pair to there instead. Okay. So so your marks are going to be 1 mark for the bond, 1 mark for the charges, okay, and 1 mark for the lone pair. Okay, so you've got those marks in your exam. Really, really important. Not a hard thing to do. Okay, and don't miss out on those marks. So that's how you do a hydrogen bond for your exam. So I've left this on for our next drawing. So our next drawing is going to be to do with volatility. So volatility is to do with the alcohols hydrogen bonding to themselves. So we've got one here that we can do a reference from. So now why don't you use that and use that as a reference, stop the video and draw it for yourself. Okay, so we're going to come over here and I'm going to draw the alcohol. Now we're talking about volatility, so the ease at which it evaporates. Okay, so to do that, let's start with the lone pairs this time. Okay, lone pairs, charges. Okay, now I'm going to draw another alcohol that lines up with it. So I want a H to line up because a hydrogen bond means a H bonding to an O, N or F, N, O or F. Okay, so there you go, and there is going to be my other alcohol. I've lined up the H and the O, then I'm going to do my charges again, and then I'm going to do my hydrogen bond. That's it. Okay, so that is your hydrogen bond between 2 alcohols, which will affect, is a strong force attraction, which means compared to alkanes, they have higher boiling points, okay, and their volatility therefore reduces compared to the alkane. So you've got to get very used to doing these kind of diagrams. So we're now going to talk about clean combustion of alcohols. So they cleanly combust, which means that in this country, in the UK, the petrol that goes into some of the cars, most of all of the cars really, is called E85. Now E85 basically means 15% ethanol and 85% petrol. So we have ethanol in it to try and make it cleaner, so 15%, but in some countries they have even more than that. Okay, so because they're clean burning, they don't produce any carbon or carbon monoxide. Well, they shouldn't do anyway. So that's why you see when they kind of burn blue. So if you look here though, let's look at the balancing, because you're going to have to balance in the equation. Now you can use halves. This is the important thing. What you've got to remember is the O is here. So when you count in your oxygens, the O is there. So let's start with the first one. So you put the 2 over there, you put the 3 over there, 1, 2, 3, 4, 5, 6, There's 2 hydrogens over there, so 3 times 2 is 6. We've got the same hydrogens. Then, counting that oxygen already, okay, we need to balance the oxygens. So 4 here, and that's 7. So we've got 7 on this side. 7 take away 1 is 6. So we need 6 oxygens here, which is a 3. Okay, so it's that type of thing. Just don't forget the oxygen. And you can go all the way through like that. And you've got your halves there. And I've seen these questions in the exam. Okay, they're simple 1-mark questions they want you to do. Okay, so make sure you can do them. Now remember, it's clean, only produces CO2 and H2O. So let's look at primary, secondary and tertiary alcohols. Okay, so you've got to recognise these, especially for the next part when we do the reactions. Okay, so first off, we start with the primary. If you look at the primary, okay, it's only got one group coming off the O. So one group coming off the O, because it's one group, okay, which is this line, and you can look at it as lines. So there's one line coming off the carbon that's connected to the O. So you're looking at this carbon here, connected to the O. How many lines are coming off it? Well, there's only one. Okay, because there's only one group. If there's only one group, it's a primary. Okay, and it's off that carbon. So one group. Now go to the next one. You can see this carbon coming off the oxygen has got 2 groups on that carbon, therefore it's secondary. Okay, and therefore that is secondary, as I said. Tertiary is going to have 3 groups. So we look here, there's the carbon we're looking at. Okay, 1, 2, 3 groups. Okay, so that's a tertiary alcohol. And if it's done in skeletal form, you literally are just looking for the number of lines that come off it. Okay. And that's the easiest way of doing it. Now let's move over to the next part, which is oxidation of alcohols. I'm going to show you this in the lab straight after this, and you'll see me looking a little bit younger because I did the lab video about 2 years ago. Okay, so if you look here, you can see primary alcohols going to aldehydes. So use an oxidizing agent, Cr2O72- H+. That's also can be called potassium dichromate, and that can be called sulfuric acid. Okay, we've just shortened it, taken out the potassium, taken out the sulfate. Okay, because they are spectator ions. Okay, we're going from primary alcohol to an aldehyde using this kind of stuff. Okay, and you can represent that as an O when you're doing balanced equations. So you can use words, like I've said, like this, or you can use the full amount, the full formula down here. Or you can just use, like I said, the words acidified potassium dichromate, just to show you what the reactant is. Now this oxidation of the alcohol to the aldehydes, okay, is usually done at your stage in displayed formula. So look at displayed formula, and what we can see here is the displayed formula is being added to the oxidizing agent, and it's one oxidizing agent to oxidize an aldehyde. So 1 to oxidize an aldehyde, so we just have 1 there. Okay, that oxidizes to the aldehyde, and hopefully you can see that this part is the aldehyde here. Okay, now I want you to look at this molecule and count the hydrogens, and then look at the next molecule and count the hydrogens. What you'll notice, and I'm giving a dramatic pause here to allow you to do so, you will notice that there are 2 extra hydrogens on this side, in which I've put in green. Those 2 extra hydrogens were here, okay, so we're on this bit here. That means those hydrogens have left. Now, hydrogen oxidized is water. So therefore, those 2 hydrogens, which I've just put over the other side, are oxidized, and they're the green ones, and they become water. Okay, so that means a simple rule for this is when you're oxidizing to primary alcohol to aldehydes, you have 1 oxidizing agent and you create 1 water, always. Now, if you have more than 1 primary alcohol, you double it, for example, if you've got 2 primary alcohols. All right? Anyway, to do this, you do distillation. So taking a primary alcohol to an aldehyde is 1 oxidizing agent and 1 water. Okay? So it's really, really important that you can do this. Now, I'd like you now to go to the lab, and I'll show you what it's like with a different haircut in the lab. So we're now in the lab to do oxidation of a primary alcohol to form an aldehyde. The primary alcohol we're going to use is 2-methylpropan-1-ol, and we're going to use dichromate, the Cr2O72-, which has this vivid orange colour, which you have to remember. Now this orange colour, when it is oxidizing the alcohol, is going to go to green. and hopefully you'll be able to see green when you look at this reaction which we set up here. So what we've got here is our dichromate, our alcohol in there, and we're boiling it, and it is evaporating up the tube. Now, here's the important thing. I'm going to show you some boiling points, and as you can see, the aldehyde has a boiling point of 63 degrees Celsius, whereas the alcohol and the carboxylic acid, which are the other two reactants and products that can occur in this, they are higher, 108 and above. So that means as long as we boil this to below 108, we'll only collect aldehyde. And the reason is because aldehydes have permanent dipole-dipole attractions between them, and they are weaker than hydrogen bonds. And the alcohol and the carboxylic acid have hydrogen bonds, therefore their boiling point is higher. So we can use that to our advantage to be able to get the aldehyde off because it has a lower boiling point than the other two. So if we then look at this, we can see it is evaporating, going up the tube, and we can see that our temperature that we've got on our thermometer is less than 108. So we are only going to collect the aldehyde. And then if you look here, it is condensing down this tube in the condenser, and then it is turning into a liquid in the ice bath. And the ice bath is just to make sure none of it escapes as a vapor. Now that is how you distill to make an aldehyde from a primary alcohol. And now we're going to go back into the studio to show how this can be drawn and done in the style of an exam question. So you have been to the lab and you've seen how distillation works, okay, and you've seen it goes from orange to green in that reaction as well, and that means the chromium, which is in a +6 oxidation state, oxidation number, going to a +3 oxidation number or state. Same thing happens in this one, and this one is primary alcohols going to carboxylic acids. Now, you can see here is the reaction for aldehydes. So you can see primary alcohol going to an aldehyde. You've got a water here. You've got one oxidizing agent. Now we're going to keep it in the same vessel, because in distillation we separate out the aldehyde from the oxidizing agent so that it stops oxidizing. In this way we're going to do reflux, and we'll show you this in the lab as well in a minute. Okay, and that reflux keeps everything in the same pot. Because it's in the same pot, that means all of this oxidizing agent is still reacting with this aldehyde, so it oxidizes it even further. Okay, so if it oxidizes it further, you'll need another oxidizing agent, and you make a carboxylic acid. Now, if you count the difference between here and here, so you count the difference, you can see that there is the same number of hydrogens, so we don't produce another water. Okay, so there's 6 hydrogens here, and there's 6 hydrogens here, so we don't produce another water. So the overall, okay, if you can count this, you can do an overall reaction going straight from here to here, because this is an intermediate. So just have a think, what could that be? Okay, so let's do it. You've got 2 oxidizing agents, okay, and you've got 1 water, and let's pull it all together. Okay, there we go. So we're doing reflux, we're doing it with a primary alcohol, 2 oxidizing agents, 1 water. And depending if you got 2 primary alcohols, you would have 4 oxidizing agents and you'd have 2 waters. It's that type of thing. Remember, it goes from orange to green as you go along. Okay, so that's how you do primary alcohols to carboxylic acid. Now, reflux. Reflux is used for this, to ensure that the oxidizing agent never leaves your reactant, so it oxidizes it fully to a carboxylic acid, but it also can be used in the next one. Okay, so let's go for the next one. We have got secondary alcohols to ketones. Okay, so when you've got ketones that are made, ketones can be made is a C double bond O. We'll show you this in a minute. You can take a secondary alcohol, remember 2 groups attached to that carbon in the center, and we can add an oxidizing agent, just 1, and we can make a ketone. You can see this ketone here. Ketone is just when the double bond O is in the middle of the chain, and an aldehyde is when it's on the end of the chain. Okay, so we've done the aldehydes, we're now going to go to the ketones. So the ketones, okay, can be made from a secondary alcohol. And again, let's do the counting, shall we? Okay, let's look at these hydrogens here. There's 2 hydrogens here, and those 2 hydrogens are completely gone here. Okay, they're completely gone, which means the 2 hydrogens are going to be floating around the oxidizing agent, and that means you're going to get some water. Okay, 1 oxidizing agent and 1 water. So a secondary alcohol is going to go to a ketone, and it's 1 oxidizing agent and 1 water. And again, if you had 2 ketones, you'd have 2 oxidizing agents and 2 waters. So very, very important that you can show that and do that. And remember, the color change is orange to green. Now let's go to the lab and actually see what reflux is, because reflux would be used for this. Now, the example we're going to do is the oxidation of a secondary alcohol, propan-2-ol. So we have propan-2-ol here. See, it's a colourless liquid. And then we have our oxidizing agent. Our oxidizing agent is acidified potassium dichromate. And you can see this is orange. Okay, you will need to remember that colour change that we have during this experiment. And it is cancer causing, hence I've got gloves on. Okay, and it's really important if you do this in the lab, you've got the lab coat, you've got the goggles, and you've got your gloves on. We're also going to use anti-bumping granules to make sure the liquid doesn't bump up the tube. So what we have is propan-2-ol, and we can represent our oxidizing agent with square brackets and O, and then that makes our ketone and also makes water. And that's your balanced chemical equation that I would expect in the exam for this reaction. Now let's move on to the actual condenser itself. If we're drawing this, we're going to have to label the condenser, we're going to have to label the round bottom flask, and when we go into the next version of this, when we're heating it all up, we'll have to label the heat as well. But before I do that, I want to show you the water in and water out. So the water in is at the bottom. And what happens, and I'll show you right here, is as I put the water on, you'll see that the water goes up and then it forces all of the air out. And that's what you want it to do. And I'm going to put it on a bit stronger just to force all of the air out. There you go. You can see all that water's now forced out. And then I'm going to put the flow right back down so it's really, really small. You can see this outer kind of casing is full of water now. So it's very, very cold, and there's no air bubbles, and that's why we fill it in from the bottom. So if you're doing the exam, water in from the bottom, water out from the top. So what we're going to do now is we'll put all of our chemicals into our reflux apparatus and show you the full setup. We've now done the whole reflux setup. You can see that we have our heat-proof mat, we've got a tripod and a water bath. And you often use a water bath. You can also directly heat it with a Bunsen burner, but you have to be really careful with that. And we are heating it using that Bunsen burner to get this evaporation and this condensation. So it's evaporating from here, and then you can see it condensing as well. Now, really important thing is that when you're drawing this in the lab, you can draw that Bunsen burner as an arrow and just write heat by it. You don't have to draw the Bunsen burner, and then obviously you have to label the round bottom flask and the condenser and your water in at the bottom, water out at the top. Okay, but the really important thing here is that why do we do this reflux? We do this reflux to make sure that the reactant doesn't get away from the oxidizing agent, so it's fully complete, the reaction is fully complete, and we also do it so that the solvent can't escape because it evaporates and then condenses, and the solvents are often flammable, so it's much, much safer to keep the solvent trapped within there. And those are 2 reasons why we use reflux. In this case, we want to push that propan-2-ol all the way up to propanone. We want all of it to react, and so therefore we choose reflux to keep all of those reactants together. What we're going to do now is take you back to the studio, and we will show you this in the form of an exam style question and answer. So now we're going to look at tertiary alcohols, and they literally just can't oxidize. So they can't oxidize, there's no hydrogens to leave, and let's have a look at one. So you need 2 hydrogens to make this happen. So every time you've seen 2 hydrogens leave when you oxidize it, apart from when the aldehyde went to the carboxylic acid. But you need those 2 hydrogens to leave. So you've got 1 hydrogen here, down here, and a big carbon containing group up here. So you haven't got 2 hydrogens to leave, therefore nothing happens. Okay, just 1 hydrogen, nothing happens. That means your colour change doesn't happen and the colour stays at orange. Now, differentiating primary, secondary and tertiary alcohols. Okay, you can do that by using the reaction we've just done to try and differentiate them. So let's have a look at this. Primary, the colour change will always be orange to green. Secondary, colour change will still be orange to green, but you can differentiate the tertiary because the colour change will not happen. Okay, so remember, especially later on, that these two, okay, are the same, but this one is different. So the next one is elimination of H2O from alcohols to form alkenes. So the conditions you use are H3PO4 or H2SO4, and you can put heat in there. Heat doesn't normally get a mark, but just put it there to be safe because you normally do heat it up. H3PO4 or H2SO4, perfectly acceptable answer for elimination of H2O from alcohol. So let's talk about an example then, shall we? Okay, so I'm going to do this in two versions. I'm going to do it in displayed formula and I'm going to do it in skeletal formula for quickness. So if we do it in displayed formula, so we just go, right, okay, here we have, oh sorry, I'm doing it the wrong one. There we go, let's go for, jumped into alkene before I should have done. Okay, and then there you have your alcohol. So we've got an alcohol like that. So what happens here is the two groups here and here will join to make water. So they'll make water. And that's what you're eliminating. That means if you take away this bond and you take away this bond, these carbons only have 3 bonds, they need 4, and so we can add an extra one in the center. So there we have our ethene. And there you go, and there's your ethene. Now remember that we're making water. Okay, so we've done that, okay, but that's not how complicated it can get. So let's have a look at this, shall we? So you've done alkenes already, so we're going to make this a little bit more complicated. I'm going to go skeletal formula now. So if that's the case, let's go for this one like this, and hopefully you can see the name of this coming out. Okay, and you've got this. Now, we've got 1, 2, 3, 4, 5. That's pentan-1-ol. Now, if that's the case, you can have pentan-1-ol, and then we're going to do another one. Okay, in fact, yeah, let's get rid of that, sorry. Okay, there we go, 1, 2, 3, 4, 5, and then we're going to put OH here instead. Let's get a bit more blue on that. Okay, and there you have your two different ones. Now, think about this, right? If I then take this and I add, and I'm going to add H2SO4, or I'm going to add, and I'm going to draw 2 arrows, and I'm going to put H3PO4. I'm just trying to show you that you can put either one down. Both of them work. Okay, so both of them work. Let's make that a bit thicker. There we go. So you got H3PO4. Now, try and write out what the products would be. So I'm going to try and write out what the products would be as well. So let's put it down. So we're going to take the OH off there, so the double bond can only be here. So this is just going to be, oops, sorry about the pen. Okay, so we have got that. I've got a very squeaky pen today. Okay, so there you have it. Okay, so that's going from pentan-1-ol to pent-1-ene. Okay, now I'm going to switch pens because this is too squeaky. Okay, and then we go to this one, and we can have the double bond going that side or the double bond going that side. It depends which way. It can take a hydrogen here and an OH here, take an OH here and a hydrogen here. So it's going to take it. We're going to do 2. Okay, and I'm going to put a double bond here. And I'm going to do another one here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we're all good. Super. Right. Oh God, that's not very clear, is it? Let's just go over that again. There we go. And that's that there. And that's there. Okay. So hopefully you can see all that now. Now, I want you to think about this. There's some chemistry here, some kind of more complex chemistry here. So I've got my ones here, okay, and you might get asked a question, how many products might you create, right? So we're just doing the bottom one here. So you think there might be 2 products, but actually there's another one. So I'm going to go down here and I'm going to look at this one here. So I'm going to get to the side and look at this one here. Notice there is a group here, and there's a group here, and there are 2 hydrogens coming off, and they're 2 alkyl groups. Now you've got 2 groups that are the same type. For example, 2 chlorines, 2 hydrogens, 2 alkyl groups, right? You can call it cis or trans, and that is in the alkenes video if you've not watched it already. So this at the moment, you can see 2 groups. There's a group here, and there's a group there. They're different sides of the bond. So the bond is here, and one's going up and one's going down. So they're different sides of the bond. So this is going to be my trans. Okay, so that's going to be my trans. Now, can you draw the cis, right? So we're going to go to the cis. Let's try and get out of the way. So basically, here we go. We're going to go down, up. Done that bit. And then we can go across. And then we can point this. Instead of pointing it up, we're going to point it down. And that is going to be our cis. Okay, so we have got, let's get rid of these little things here. Okay, you've got your cis and you've got your trans. Okay, so the possible number of products you can get is not 2, it is 1, 2, 3. Okay, so really, really important when you're looking at these kind of questions, you don't miss that complication when you have an OH on number 2 of a 5 carbon, or anything basically that's unsymmetrical. I hope that makes sense. So this is our last reaction of this, which is nucleophilic substitution of alcohols to alkanes. First of all, it is a nucleophilic substitution mechanism. Look, the mechanism for this you don't need to know, but it is helpful to know. It's a nucleophilic substitution mechanism. Now, it can be done with bromine or chlorine generally. So it's sodium bromide and sulfuric acid, or sodium chloride and sulfuric acid. We've chosen to do a chloride. Okay, but you can just substitute bromine in there and bromine in there. And this is an often one which can be forgotten. So basically, you take the alcohol and you put salt, or NaCl, with it, with sulfuric acid, and you get water and you get NaHSO4, and you get the chloride. Going back the other way is sodium hydroxide. Going this way is an acid and the salt. Okay, so this is an often forgotten one, and you can be asked to do the balance equation or get it in a synthesis. Okay, so it's a good one to know. Nucleophilic substitution of alcohols to haloalkanes. And that is all of the alcohol section for first year of the course in Module 4.